So we're going to be talking about the Kerr black hole. And probably the most remarkable thing about the Kerr black hole is that it has a metric that can be written down very simply. I mean, we can fit it into one line or two. And the metric of a Kerr black hole, which was derived by Kerr in the early 1960s, is something that has two parameters in it, the mass and the angular momentum. And there's a generalization to this that was derived a few years later by Ted Newman and some of his students, and that allows the Kerr black hole to also possess a charge. So that's known as the Kerr-Newman black hole. So in all, you can have three parameters. Charge, as we know, is not terribly realistic, astrophysically speaking. So the two parameters that really matter here are the mass and angular momentum parameters of the charged black hole. So here I'm just writing down the metric, and I'm introducing some symbols along the way that I'll define in a moment. Got that. We've got rho squared over delta times dr squared, and we've got rho squared d theta squared. So that's the Kerr metric, and in terms of a few symbols, so we've got rho squared that's defined as r squared plus a squared cosine squared theta. We've got delta that's defined as r squared minus 2m times r plus a squared. We've got sigma, which is r squared plus a squared all squared minus a squared delta sine squared theta. And the only remaining thing is that A is J over M, where J is the angular momentum of the rotating black hole. So we have two main parameters here, J and M. M for obviously mass, J for angular momentum, and A is a convenient version of this, which has the dimension of length. So A is a dimension, is a parameter that has the dimension of length. So that's the Kerr metric. And as I said, the Kerr metric is something that, while is a bit messier to write down than Schwarzschild, but you can still fit it into just a few lines like this. And that's the metric that describes the space-time geometry outside any rotating black hole, no matter what its mass is, no matter what its angular momentum is. It's, it's this metric that describes all black holes. We have the same sort of uniqueness property for rotating black holes as we had for Schwarzschild. So in Schwarzschild, we had the Israel uniqueness theorem that said that the end result of gravitational collapse after the process has settled down, after the process has settled down to a stationary state, in the non-rotating case, the end state has to be a Schwarzschild black hole. Here, the statement is that in the stationary state, in the steady state after collapses occurred, the black hole will settle down to a Kerr state, and that's the metric that describes that final state. So that uniqueness theorem was established also in the, starting, around the 70s. Brandon Carter was the main driver for this, and there were others who sort of filled in some holes that he had left in his proof. Did you have a question?
Is there also like a Birkhoff theorem for this, where like instead we have cylindrical symmetry or something like that?
No. So while we don't have cylindrical symmetry here, so we have axial symmetry. But yeah, no, there's no Birkhoff's theorem in this case, and in fact, there's nothing that says. In fact, there's no reason to believe that the Kerr black hole would be the external metric to anything else but a black hole. So the Kerr metric will apply to a black hole, but if you had a rotating star instead of a black hole, in the case of Schwarzschild, we could say that if we have a spherical star, no matter what it does internally, the external metric will be a vacuum metric. Therefore, it will be, by Birkhoff's theorem, it will be a Schwarzschild solution. Here, if you have a star, a rotating star, the external metric in general will not be the Kerr metric. It will be something else. And the reason for this I'll come to in just a second. This is a rather specialized metric, and it really applies only to black holes. It will not apply to other objects, even though, I mean, it will not apply to other rotating objects. So, a couple of features that I want to highlight before I discuss the properties of the space-time. The first one is that, well, here we have off-diagonal terms in dt d phi, and that's something we recognize, from what we talked about, last week or maybe before. That's something that will produce a dragging of inertial frame. So one of the aspects of dealing with a rotating space-time is that if you fall in, the rotation of the object will drag you along in the same sense of that rotation. So that's an effect that occurs in a Kerr black hole in the same way that it occurred in the linearized gravity example that we talked about before. So the A parameter or the J parameter here will be associated with a dragging of inertial frames. That's what happens for any rotating spacetime. A couple of other things. So rho squared here is a function that's essentially positive everywhere. To get rho squared equal to 0, you have to have both this term here being equal to 0, which means that r has to be equal to 0, and that term over here has to be equal to 0. And if we fix a, we don't make a equal to 0. That would be the case of a Schwarzschild black hole anyway. So that means that the cosine theta must be 0, which means that that occurs only in the equatorial plane of the black hole, where theta is pi over 2. So the reason I'm mentioning this is that, well, we have a couple of places in the metric where things indicate singular behavior, one of which has to do with when rho squared is equal to 0. We see that this blows up, this goes to 0. And in fact, rho squared going to infinity signals the occurrence of a true space-like singularity, and that's a singularity that will occur deep inside the black hole. The remarkable thing about this is that this singularity is actually directional, because if you don't live in the equatorial plane, if you don't move in the equatorial plane, rho squared has no chance to become 0, and therefore, as far as you're concerned, there's no singularity inside the black hole. You only see the singularity if you approach it from the equatorial plane, which is a fairly remarkable thing. Something that we didn't see in the Schwarzschild case. Of course, the spherical symmetry in that case meant that if we approach the singularity from any direction, we hit it in exactly the same way. Here, to hit a singularity, we actually have to approach it from the equatorial plane. If we approach it, if we approach it from the axis, for example, we'll never notice that the singularity is there. I'll come back to that in a second. That's certainly a remarkable property of the Kerr solution. In fact, I might as well tell you now, the singularity is shaped like a ring. In the Kerr black hole, the singularity is shaped like a ring. So if you approach the ring from the equatorial plane, you hit it. If you go through the ring through the axis by going along the axis, well, you can avoid it unless you approach it from head on like this. But if you go through, you'll never notice it's there. And along the lines of what we talked about for Rice and Nordstrom this morning, there are ways of avoiding the space-like singularity. Avoiding the singularity in the Kerr black hole, and we'll see also black hole tunnels and various things like that occurring for the Kerr solution. The other place where we seem to have a singular behavior is where delta goes to 0. And delta going to 0 is not a genuine curvature singularity. It's, again, a problem with the coordinates, and it can be cured in exactly the same way by constructing Kruskal-type coordinates that go through the places where delta goes to 0. Delta going to 0 is basically is going to be the place where we have the event horizon. But here also, delta going to 0 means that we have a quadratic equation here to solve, and that means that we also have an inner horizon in the same way that we had one in the Rice and Nordstrom case. So all of that is sort of contained here, but I want to unravel all of this systematically and talk about the important features of the Kerr solution. I won't give a lot of details here, but I'll talk about the essential features. Okay. Let me go back to what I was telling you before. So the Kerr solution applies only to a black hole state. And it is not an exterior solution to any rotating star. The reason is that, well, it only has two parameters, m and j. And imagine if you had a rotating star. If you have a rotating star, of course, it will have a mass and it will have some angular momentum. But the star being in rotation means that it's going to be deformed. It's going to be centrifugally deformed by its own rotation. So it's going to be flattened at the pole. It's going to be bulging at the equator. The way to describe this, well, there are various ways you can describe the deformation, but one convenient way to describe the deformation, if we think about doing this in Newtonian mechanics, in Newtonian gravity, would be to calculate all the multiple moments that characterize the deformation of the body, starting at quadrupole, continuing at octupole, and all L equals 4, L equals 5, L equals 6, and all of that. And those multiples would basically provide you with a characterization of the internal structure of the body, the exact way in which it's deformed, that depending on exactly how the matter is distributed within the body, what the rotation is it rigid rotation, is it differential rotation, all of those details would basically go into the calculation of all the multiple moments. And in general, a rotating star would have a gravitational field, would have a mass distribution that will give rise to a whole sequence of multiple moments and a gravitational field that would basically carry this dependence on the multiple structure of that body. So through the multiple moments, basically, we end up with a characterization of the gravitational field for a rotating star that involves a lot more details than just two numbers, m and j. All the quadrupole moments, all the multiple moments are basically independent from each other, and they're additional pieces of information that you need to provide in order to have a full characterization of the gravitational field outside. With the Kerr solution, we only have two parameters to play with, which means that all the multiple moments are going to be very specific functions of those two numbers. So the Kerr black hole is deformed. The Kerr black hole will have, a bulging at the equator. It will have a flattening at the poles, and it will have a sequence of multiple moments that will describe how the gravitational field behaves outside of this. But those multiple moments will be a function of only two numbers. Whereas in the case of a rotating star, those multiple moments would be a function of all the details that go into internal structure. So for that reason, basically, for any random rotating star, you will never be able to match the exterior solution to a Kerr state because the multiple moments will not match. If you were to fine-tune all the moments so that they match the moments of a Kerr black hole, you could maybe concoct, a rotating solution or a rotating star that would have just the right, distribution of matter, the right amount of differential rotation, the right amount of everything, to produce the same sequence of multiple moments as would be the case for a Kerr black hole. But that would be a very, very specific star, and any other star will not have this match. And basically, that's the reason for this, the really fundamental reason why the Kerr black hole is not like Schwarzschild. It doesn't apply to the exterior vacuum outside a rotating star. As far as I know, no one really has managed to construct a stellar model in GR, including rotation, that would reproduce a Kerr exterior. I mean, it just doesn't work. No one has found the right ingredients or the right way of doing it. And it's not surprising. You would have, really to produce the right sequence of multiple moments, you would have to provide an infinite number of pieces of information to specify just, exactly what the radial, what the distribution of matter inside your star would be, what the rotation distribution would be, So you would have to fine-tune all of this in order to find all, all the moments matching, and it's just basically plain impossible to do that. Okay, so that's one thing. That's one thing that I think is important to understand. Another property of the Kerr solution is the fact that we have two killing vectors. So that's good news, because that means that a lot of the properties of the Kerr solution can be discovered using the killing vectors as a way to simplify things. So we have a time-like killing vector, T alpha beta, which in this coordinate system here, which is known after Boyer and Lindquist, is just given by the time direction. So that's the time-like killing vector. And I should put time-like in quotation marks because as with Schwarzschild, we'll see that its signature changes sign as we move in the space-time. And we also have a rotational killing vector that's purely in the phi direction. And what that means is that we have a stationary and axially symmetric spacetime. So the Kerr state is actually pretty simple because it has a guaranteed built-in axial symmetry in it. Something that, again, is a bit surprising, because the initial star might well have been highly non-axially symmetric, but by the time the collapse has occurred, by the time that you've radiated all of the extra, structure to the star, the final state after things have settled down is an axially symmetric state. So that's pretty interesting. The existence of those two killing vectors means that, if you think back about what we were doing in terms of defining mass and angular momentum in terms of Komar integrals, well, you can apply all of this, and that's the way to confirm that M as defined here, as used here in the metric, and J as defined here are really, they really correspond to those formal definitions we had for mass and angular momentum. So those parameters really have some meaning to them. All right, let's look at the time-like killing vector and see where it changes sign. So, so if I look at the norm of the time-like killing vector, I'm really looking at the GTT component of the metric, and I can write it down over here. It's 1 minus 2m r over rho squared, which goes to 0 when, well, rho squared is equal to 2m rho, which means that we have a nice quadratic equation for r squared. So r squared minus 2mr plus a squared cosine squared theta is equal to 0. So there's going to be a place in the space-time given by r, the solution, the outer solution to this equation. Let's see if I can do this in my head. So r is going to be 2m plus or minus 4m squared minus 4a squared cosine theta divided by 2. So it's given by m. I'll take the outer solution, m squared minus a squared cosine theta. I hope I agree with my notes here. Yes, I do. That's good. So there's a place given by this relation over here where the norm of the killing vector goes to 0. So thinking back about Schwarzschild, well, we had this behavior in Schwarzschild as well. So we might think, well, that must be the place where we have an event horizon. Because in Schwarzschild, we had also the event horizon as being the place where the killing vector was turning from time-like to null, to space-like inside the black hole. This is not the event horizon. And the test for this is to verify that this surface defined by this relation over here, that surface is not the null surface. The surface R equals all of this is not null. So this is a place where our time-like killing vector is null, but it's not tangent, or it's not that vector is not hypersurface orthogonal. So the surface where it goes null is actually not a null surface. So the vector is not lying on the hypersurface. We don't have a hypersurface orthogonal situation here. So what's the meaning of this? Well, the meaning of this is that, well, here's a place where if you're inside that surface, you will not be able to stay in place in the space-time. Because if you were able to stay in place in the space-time, that would mean that your word line is going to be an orbit of the killing vector. Your four velocity will be aligned with the killing vector. And that's fine as long as the killing vector is time-like. You can align your four velocity with the killing vector as long as it's a time-like vector. But inside that surface, it's no longer a time-like vector. It's a null vector. It's a space-like vector inside the surface. And there's no way you can align your four velocity along a space-like vector. So that surface, it's called the static limit. It's also known as the ergosphere. And it's basically the last place, or the innermost place, where a stationary observer, a static observer, can exist. So just to draw a diagram, if this is the axis over here, the ergo sphere is shaped a little bit like this. And well, this is the surface R equals blah, blah, blah. And this is the pole. This is the angle theta. Never mind that. And basically, if you're out here, you can have a static observer. And a static observer would be such that the four velocity would be a normalized version of the time-like killing vector. So a static observer, again, is an observer that's going to be aligned with the time-like killing vector. But a static observer, as you bring the observer in, would have a harder and harder time maintaining a static word line. And in fact, at that surface, it would fail because this vector is turning null, while this vector, of course, has to remain time-like. Beyond the surface, T is space-like, and of course, there's no way that an observer could be still static because that observer would be moving with a speed faster than the speed of light. So what's going on? Well, what's going on is that as you approach the surface, the dragging of inertial frames becomes so powerful that you cannot prevent yourself from going along with the rotation of the space-time. The observer is trying to maintain a static situation, but fails because the dragging of inertial frame compels that observer, him, to move along. And if there's, if the observer basically starts moving in the direction of rotation, well, that observer is no longer static. And inside the ergo sphere, inside the static limit, all observers must be moving in the direction of the black hole. So all observers will be basically dragged by the black hole. They will not be able to avoid moving along with the black hole. So a static observer is fine outside. Inside, we can't have a static observer. Inside, we have that all observers are dragged by the black hole rotation. All right, so that's an interesting place. And inside the ergosphere, inside the what's called the ergo region of the black hole, of the space-time, we have a place where the time-like killing vector is space-like. And remember that to a time-like killing vector, we normally associate a conserved quantity if we're talking about particles moving on geodesics. And a particle falling in the ergo region, or a particle moving inside the ergosphere, or inside the, within the ergo region, has the ability to have an energy that can be either negative or negative. Because if your killing vector is space-like, there's no requirement that it be, if the killing vector is time-like, of course, the energy has to be always positive, because that's the statement that the inner product between the velocity vector of the particle and the time-like killing vector has to be, well, it comes from the statement that both vectors are future-directed, and therefore the energy has to be positive if you define the energy this way. But if this is a time-like vector and this is a space-like vector, the sign of this can be anything you want. This as the interpretation now of a momentum instead of an energy, and the momentum can either be pointing this way or that way, so it can have either sign. But this quantity here always has the interpretation of being the energy that a particle would have at infinity if it could make it to infinity. And that energy for that particle inside the ergo region can be of either sign. So if we pick the negative sign, the statement is that we have the ability in the Kerr spacetime of generating particles with negative energy, with the understanding that this would be the energy that they would have if we could bring those particles out to infinity. And the point is that we can't, because if they have negative energy, they're confined within the ergosphere. They cannot be propagating out to infinity. But that's enough, though, because if particles can exist inside the ergo region with negative energy, you can come up with processes that would allow you to extract this energy. That's the Penrose process. And it's a very simple idea. Throw in a particle with positive energy, it goes in, let it decay into one particle with negative energy, and another particle that will have more energy than the initial particle, because energy is conserved here, right? So you give this particle some energy, this takes away energy, therefore by energy conservation, this will have more energy. So this is energy, this is positive energy, this is more positive energy, this is negative energy. That particle will be stuck inside, will never come out again. That particle with positive energy can come back out. So what do you have? You have a process by which you feed some energy to the black hole, but you come out of it with more energy than before. So the Penrose process is all about extracting energy from the black hole. So you keep repeating this, and you keep extracting more and more energy from the black hole. And that's a perfectly viable, perfectly fine mechanism, at least as a matter of principle. But there are some astrophysical, manifestations of this that probably are responsible for, extragalactic jets and various things like that. There's a limit to this because, if you examine this a little bit more, and I do that in the book, if you examine the process, the Penrose process more closely, you find that as you extract energy from the black hole, you're also reducing its angular momentum. So that process extracts energy, but it also reduces the angular momentum of the black hole. So an interpretation of this is to say that what you're actually extracting is the rotational energy of the black hole. And each time you do that, of course, you reduce the rotation of a black hole, you reduce its angular momentum, and eventually, as you keep doing this, the angular momentum will go to zero, and then, the Kerr black hole will reduce to a Schwarzschild black hole, and the ergo region will disappear, and you'll lose the ability to do that. But potentially, there's a lot of energy that you can mine from a black hole. You can extract all of its rotational energy through a process like this, and again, that's something that may well be manifested in astrophysical processes, but it's more complicated in astrophysics because you have to sort of use magnetic fields to pull this off. You have to have accreting matter and things like that. But it's probably a variation, or at least a loose there's a loose connection between what happens in astrophysics and the Penrose process. So all of this basically is courtesy of the existence of an ergo surface and an ergo region within that surface. So that's kind of cute. So what happens if we go beneath the ergo region? So let's do that. So let's explore that a little bit more. If we go inside and we keep moving in, so first of all, now we're going to be dragged forward by the rotation of the black hole, something that we could fight outside of this surface, but no longer now. Inside the surface, we can consider what's called stationary observers. Those would be observers that feel the drag of the rotation, so they let themselves be dragged because they don't have a choice, but they're moving purely in the angular direction. And if you're moving in the angular direction, well, you have to, first of all, but if you're moving only in the angular direction, the black hole is axisymmetric, so you don't see, as you move, a change in the gravitational field. So that's why they're called stationary observers. A stationary observer will have a four velocity that's going to be a normalized version of this vector over here, which is just a statement that you're moving in a time direction because you have no choice, but you're also moving in the angular direction, and the omega in front is basically just d phi dt. It's the angular velocity. So that's what I mean by stationary observer, an observer that has a constant angular velocity feeling the drag of the black hole. There's going to be a bound on omega that's going to come from the requirement that this be a time-like vector. So this is a vector that we now know is space-like inside the ergo region. This is a vector which is also space-like. And now I'm wondering, how can it be that the resulting vector is time-like? Okay, I'm kind of surprised here. So apparently the sum of two space-like vectors can be a time-like vector.
It's possible.
Yeah?
If you have two space-like vectors, then the sum becomes time-like.
Right, two vectors that point in very different directions like this, and then the sum is, yeah, you're right. Oh, thank you. Okay, it's not that strange after all. Okay, so yeah, so here inside the ergo surface, this is a space-like vector, another space-like vector over here, but we still want u to be a time-like vector. But the point is that, well, this will only be true if, and it's just a consequence of the algebra here. It's only going to be true if omega is going to be confined within a lower bound and an upper bound. And so basically, what we find is that so for u time-like, it has to be. I'm not going to I'm not going to do the algebra here, but it turns out that there's going to be some lower bound on omega, and there's going to be some upper bound on omega. And of course, right at the ergo surface, we know that the lower bound has to be 0, because the observer must be dragged along with the rotation of the black hole. And the point with this is that as the observer keeps moving in, I'm going to try to redraw this here. As the observer keeps moving in, So I'm considering, say, a sequence of observers here. So the observer is moving along in the angular direction, but I'm taking a sequence of observers where each observer basically is brought in closer and closer. What's going to happen, and that's something that, again, I have to rely on the algebra to flesh out, but I'm not going to present the details. What you find is that this bound gets increasingly narrow. So you get squeezed in. And there comes a point where it gets so squeezed in that there's only one possible value at which you can rotate around the black hole. So there's going to be an R. So the interval shrinks as R decreases until omega minus equals omega plus equals some limiting value, omega h, that you can read off if you were to go through the algebra. And that limiting value is given by A divided by, I haven't defined it, but I'll do that in a second, R plus squared plus A squared. And at that point, the dragging of inertial frames is such that all observers co-rotate together as they approach this inner limit, this inner surface that is reached when we reach the situation. And that's a place, in fact, where this vector also becomes null. Not this one. This one is prevented from being null. This one here is going null. So in that situation, T alpha plus omega h phi alpha is null. And at that point, in this limiting case, basically, even stationary observers can't maintain their time-like killing vector. So here you reach a point where something really dramatic has to happen. And that's where the black hole event horizon is. So inside that surface, there's another surface which is the event horizon. So this is the static limit. This is the event horizon. And the event horizon is located at R equals R plus, which is given by M plus M squared minus A squared. So you penetrate the surface, you're dragged on. And if you keep going in like this, you're dragged on more and more. And if you reach this limit over here, if you're just above the event horizon, you find that you're compelled to rotate at one specific angular velocity, which is basically associated or identified with the black hole's own angular velocity at the event horizon. And at that place, in the limit where you reach that situation, you reach that surface over here, you find that, even to maintain yourself there, you would have to move faster than, so you cannot maintain your time-like for velocity here. So an observer right here, basically, in order to keep a time-like trajectory, will have to just fall in. And once you've fallen in, there's no turning back. That is the event horizon of the black hole. This is a null surface. This, by the way, happens to be a solution to delta going to 0. And R plus is the outer solution. There's also an inner solution, R minus. And in order for all of this to make sense, it has to be that the angular momentum of the black hole is bounded from above. You cannot have a black hole that has more angular momentum than mass, in this representation here. So A is smaller than M, which means that J has to be smaller than M squared. Otherwise, you may have a Kerr solution, but you don't have a black hole because you have those. So basically, what would be coordinate singularities in the case where all of the solutions are real would become curvature singularities. They would become, so that would become a highly singular object if you didn't have this bound on angular momentum. So all rotating black holes can only rotate so fast, and beyond that, they wouldn't be a black hole. You wouldn't have a black hole state if you were to violate this bound over here. It's sort of the same story that we talked about when we were talking about overcharging a black hole. If you want to overspin a black hole, you would have to send some stuff with angular momentum. But as you send stuff with angular momentum, you're also sending in mass. And as you keep approaching this limit, you find that it's increasingly hard to overspin the black hole, although recently there's been some papers written to suggest that maybe there's still some way, there's still some open region in parameter space where you can overspin a black hole by throwing in a particle with a little bit too much angular momentum. So that's still a topic of research that people are pursuing these days. But other than that, there's some confidence and some reasons to believe that in astrophysics, at least, black holes can rotate up to this limit, but not beyond that. All right. So basically, two things have gone on here. So if you're dealing with static observer, there's a limiting surface beyond which static observer cannot live. That's the ergo surface. That's the place where the time-like Keeling vector goes null. This is, and beyond this, you have the event horizon, and that's when this vector over here, which is a linear combination of Keeling vectors, and that by itself is a Keeling vector, that's where this vector goes null, and that's where the event horizon of the curved black hole is. That's the positive root, or the outermost root of this equation here where delta goes to 0. There's also an inner root with the negative sign over here. So inside the curved black hole, we also have an inner horizon that on this diagram would look something like this. And that would be analogous to what we had in the case of Rice and Nordstrom, where we had both an outer horizon and inner horizon. And presumably that means sort of similar things regarding what the internal structure of the solution would be like. And I'll draw a Penrose diagram in a few minutes that sort of captures all of these things. All right, so any questions about these things so far? All right. So we talked a little bit about the Penrose process, something that obviously can occur in the region between the ergo surface and the event horizon. Once you're inside the event horizon, of course, you cannot get anything out of this. So we've talked a little bit about that. We talked about the dragging of inertial frames, and we've talked about the existence of two horizons. So the horizon at delta equal to 0 produces a coordinate singularity that's very analogous, very similar to what we had for Schwarzschild. And the cures for that are very similar. And one way is to basically go the Eddington-Finkelstein way, where you look at the behavior of ingoing light rays, and you try to attach a coordinate system to those, and you write the metric in this new coordinate system. So that's something that is fairly easy to do. The only complication is that, well, all of those light rays now, light rays like time-like observers, will be dragged by the rotation of the black hole. So basically, the light rays that you have to consider when you do this construction are going to be light rays that are dragged forward by the rotation of the black hole. So that introduces a little bit of complexity in the construction. But you can construct coordinates like this, coordinate systems like that, that will allow you to re-express the metric in such a way that you can continue across the outer horizon. There's also a version of the Kruskal coordinates that you can construct. They're very similar to what you would do for Schwarzschild. So you can do that as well, but that tends to be a bit more complicated, and it can be done as well. So if you read the relevant sections in the book, you'll see that I do all of those things. And there's some algebra involved. There's some technicalities that have to be dealt with, but it's more or less along the lines of what we did for Schwarzschild. Bottom line is that you can take the curve metric and you can extend it beyond each horizon, and you can do sort of thought experiments the way we did this morning when you look at the motion of the observer and you see where does it go. And the same sort of things seem to occur inside Kerr. You have one crossing of the event horizon. You have one crossing of the inner horizon. You have a turnaround. You have a turning point. You have a second crossing of the inner horizon, second crossing of the event horizon, and you have the same sort of black hole tunnels that seem to exist this morning. We got rid of them this morning. We'll do the same here. But there's the same sort of rich internal structure that we get from the pure Kerr solution that is very similar to what we had for Reissner-Nordstrom. So let me just draw a Penrose diagram that describes all of this. It's kind of cute for sure. It's kind of cute for Kerr. So for Reissner-Nordstrom, I was drawing singularities. That's how I always start my drawing. But here, I'm not going to do that. I'm going to draw a dash curve. But other than that, I'm going to make pretty much the same drawing I made this morning. And I could continue it over here. I could continue it down here if I wanted to, but let's stop here. So as with Reissner-Nordstrom, well, we have an external part to the space-time, which is over here. So this is my scry plus, this is my scry minus. This would be R plus. One copy, the other copy. This would be R minus, one copy, the other copy. This would be a third copy of R plus. And continuing beyond that, we would have another copy of our asymptotic universe after going through the tunnel once. But it's a bit more interesting than that. This is where the singularity of the black hole is. But now, remember, we talked about this a little bit before. The singularity is actually directional. If you avoid the singularity, you can avoid the singularity by not moving in the equatorial plane of the black hole. You can approach the black hole from any direction. You don't have to pick the equatorial plane if you don't want to. If you approach the black hole through the equatorial plane, this is the singularity that you'll encounter. And it's pretty much the same sort of singularity that we had for Reissner-Nordstrom. It's time-like, like it was for Reissner-Nordstrom. If you approach it through the axis, you don't see the singularity. You're going through the ring. And in that case, there's nothing stopping you here. You can just keep going. And you end up over here. This is a weird place. So it's another asymptotic region that is different from the first one we had up here. It's different from the one we started with, obviously. So that's the region you get to if you go through the ring, singularity, and keep proceeding. And if you keep proceeding, you'll find that, well, as we saw before, so here there was a turning point. You go through R plus, you go through R minus. This is almost R equals 0. But there's a turning point that's going to take place, and motion beyond this is going to be proceeding toward large values of R. And in fact, you'll find that over here you have another asymptotic region with its own scry minus and its own scry plus. I don't think I'm going to be able to justify this here. But in this region, if you were to look back at the black hole you just left, you would find that this black hole has a negative mass. So the perception over here is that you would be in a space-time with a negative mass object. See, when you're escaping this way, you're not encountering other horizons. In fact, I think the way it goes is that R keeps on decreasing, and in fact, there's nothing that stops you from going into negative R regions. This R over here, rho, is something that basically plays the role that R used to play for Schwarzschild. This R is not restricted to be positive. And in fact, this is the region where it goes negative. We're entering the region of negative R. Yeah, and that's how it works. So you keep on decreasing in R, so you're not really encountering a turning point. Sorry for saying this before. As you keep going through the ring, you find that you're basically accessing a region where R is negative. And if R is negative, when you look at the metric, if you look at the metric asymptotically, rho squared asymptotically will behave as R. So here you get R over R squared, that's 1 over R. But if R is negative, you pick up a different sign here. And if you reinterpret everything in terms of usual coordinates, you will find that it's as if you were living in a region of space where mass is negative. So that's a pretty weird place in the Kerr spacetime where inside the black hole there's another asymptotic region. You're not outside the black hole. It's not like this one over here where you came out of the black hole. Here you're still inside the black hole. You go through the ring. You look back. It's as if you're dealing with a negative mass object. But you can go all the way to R goes to minus infinity and live comfortably in that region inside the black hole and look at your object behind you that has negative mass. So that's pretty weird. Another thing that can occur around the ring singularity in this region over here, I'm not sure if it's shaped like this, but it's somewhere along there, is that you can have curves with closed time-like curves. You can have time-like curves that go back on themselves. And that has to do with the fact that G phi phi, when you look at this closely enough, you find that the coefficient of G phi phi can change sign somewhere around there. And if G phi phi changes sign, that means that the phi coordinate, essentially becomes time-like. And so that a periodic curve, as phi ranges through 2 pi, has become a time-like curve that's closed. So there's a tiny region in here where those closed time-like curves exist. So that's pretty weird, even weirder than anything we talked about when we talked about Reisner-Nordström. All the other weirdness that we used to have, so those observers that can cross in and reemerge outside the black hole tunnel into another asymptotic universe with a positive mass black hole in it, that's still there. But all of the other effects that we had to take into account to sort of rule this out on the basis of not being very realistic are there also. So the inner horizon instability is still here. So all of those processes that we talked about also exist for the Kerr black hole. So basically, again, there's no reason to believe that anything that we talked about beyond the inner horizon are physically realistic, because with a little bit of perturbation from the outside, with the pileup effect that we talked about, all of those features will basically be erased. The Kerr solution is unstable internally the same way that the Reisner-Nordström solution was unstable. And we find that, in fact, probably, in a Kerr black hole, we have a singularity forming here, as a result of the instability that will basically remove all of this crazy stuff away from the solution. So all the crazy stuff basically are artifacts of the pure unperturbed Kerr solution. There's just not any reason to believe that inside the black hole that it should be the Kerr solution that applies. It's going to be a perturbed version of the Kerr solution that should apply in physically realistic situations. And the perturbation grows big as you start approaching the inner horizon, and it will change the character of the spacetime completely from what Kerr would describe to something that's really not Kerr. So the relaxation to Kerr is still valid outside. So the Kerr spacetime is always going to be a very good approximation to any perturbed state that you would get on the outside. The instability plays inside. That's the same story as we heard this morning. And all of this crazy stuff here really is relevant only for the sort of fiction that the whole spacetime would be described by the pure exact Kerr solution everywhere. All right. All right, so the message here is that, well, the internal structure of the Kerr black hole is an even weirder version of what we had for Reisner and Nordstrom, but for the same reasons we talked about this morning, all of this are artifacts of a situation that's too idealized to be believable, and if you put in the smallest amount of perturbation and let the instability play out, you find that the internal solution deviates very strongly from the Kerr solution and probably doesn't give all of those weird features. As far as the outside is concerned, we have a perfectly acceptable solution, a very good approximation to the eventual stationary state that occurs outside the black hole. And we have the metric to describe it. That metric has two killing vectors. And we can do a lot, actually, playing around with just those two killing vectors to describe the properties of black holes. So what I'm going to start doing now is to step back a little bit. We're going to think about black holes, but in much more general terms. We're going to think of them not in terms of solutions, but we're going to think of them in terms of spacetimes that have two killing vectors and some additional properties. So the point I'm trying to make here is that we can infer a lot of stuff about the Kerr black hole by just playing around with the Kerr metric and computing things like the event horizon area, doing things like that. But it turns out that we can do these things in a much more general context where we don't have to stare at the solution. We can just stare at the properties of a space-time that would have an event horizon and two killing vectors. And that turns out to be very powerful and very neat because, even though this is quite pretty and very simple, there's still a lot of details involved in calculating anything in the Kerr metric, and we can bypass a lot of this by employing the approach that I'm just going to introduce right now. So any questions before I move on? Okay, so now what I want to do is to introduce a general discussion of stationary black holes. And those stationary black holes certainly could be Kerr black holes. In fact, we have uniqueness theorems that say that they will be Kerr black holes, provided that there's no matter outside the black hole. If we place an accretion disk outside the black hole, and if it's substantially massive, then the Kerr metric will not apply. We will have to account for the presence of matter outside the black hole, and we will be dealing then with a solution that's not going to be the Kerr solution. It's going to be the solution that belongs to that black hole surrounded by an accretion disk. I'm thinking here of a quiescent accretion disk. I don't want to break the stationarity property. I don't want to have a flow of matter that would mean a time dependence. I want to consider basically a stationary situation, but potentially with matter living outside my black hole. And in those situations, I still have a black hole. I still have a stationary and axially symmetric situation, as we'll see, but I don't have necessarily a Kerr black hole. So that's the point of view I want to take. And as you'll see, it's actually pretty powerful. So we're going to look at a stationary black hole. And here it could be Kerr for vacuum, but it could also be non-Kerr with matter. There's a theorem from Stephen Hawking going back to 72 that says that a stationary black hole is either static if it's non-rotating, or axisymmetric if it's rotating. Nowhere in the proof is there a requirement for the black hole to be a Kerr black hole. That will be true irrespective of any particular solution to the Einstein field equations. It's basically just a property of spacetimes with event horizons that have killing vectors. So a very powerful theorem. I won't prove it. It's pretty involved. I can refer you to the original paper if you want to see a proof of this. It's very clever. People back then were very clever when they were, doing all this black hole business. So a stationary black hole is either static. If it's static, that means that it's non-rotating. And if it's non-rotating and it's static, then there's only one, well, there's still two killing vectors, but one becomes more important than the other. If it's axially symmetric, then we still have, we have the one killing vector and we have the other killing vector. So basically, any stationary black hole will always have a guaranteed existence of two killing vectors. So as a result of this, we're going to have a time-like killing vector T alpha, and we're going to have a rotational killing vector phi alpha. In the static case, this one doesn't play much of a role. This one becomes the important one. In the axisymmetric case, both are important. Another outcome of the theorem is the fact that if we're dealing with the axisymmetric case, there's going to be a combination of the two killing vector. I'm going to call it C, that's going to be null on the event horizon. So that's a definition for C. A linear combination of two killing vectors with a constant coefficient is also a killing vector. That killing vector C, the statement is that it's going to be null on the event horizon. If it's non-rotating, of course, it's going to be the time-like killing vector. If this is 0, if omega h is 0, then it's going to be the time-like killing vector that's going to be null on the event horizon. In general, we're going to have a combination of time-like and rotational killing vectors going null on the event horizon. So none of this is surprising. All of this we've seen in the case of the Kerr black hole. The point here is that this holds more generally speaking. It holds for any stationary black hole. And it's a property basically of the fact that you're dealing with a stationary spacetime with an event horizon. So that's a pretty remarkable statement. And one consequence of this is that, well, I'm going to call it V squared here. V squared being the norm of the killing vector is going to be 0 on the event horizon. And, well, as usual, here we're given a null surface. The null surface is going to be generated by null rays. The null generators of that surface are going to be, this vector here is going to be tangent to those null generators. So, so again, we have the usual story of having a null surface. So the orbits of the killing vector here are going to be the null generators of the event horizon. Okay. So already we have set the stage for a lot of very powerful properties to come out of this. And I'm just going to keep extracting these things. And we're going to see that we can keep doing this without ever writing down a metric. So already the essential inputs are here. And we don't need to ever write down an explicit metric to do any of the stuff. So we have a killing symmetry. Which says that, of course, the Lie derivative of the metric in any killing vector, but this one in particular, will be 0. And that implies, in particular, that the Lie derivative of v squared is going to be 0. Because the Lie derivative of v squared will involve the Lie derivative of the metric, which is 0, and the Lie derivative of xi with respect to itself, which is always 0. So as a consequence of this, we have that this condition over here is actually preserved by the flow along the event horizon. But this is an equation that we can actually write in a different form. This tells us that, well, I'll ignore the factor of 2 here. Yeah. That's what I wanted to say. So that basically the sorry, I'm a little confused because if I do the differentiation, I get twice v Lie derivative of v, which is this derivative over here. And the problem I see is that if v is 0, then I can't conclude that this is 0. So I think I was misleading myself here when I was doing all of that. So let me just scrap this. And let me try to remember what I was trying to do instead of that. Okay, yeah, I didn't need that. Okay, sorry about that. So this is the defining equation on the event horizon. So we have a function like phi before. Now I call it v squared. That's 0 on a null surface. And basically, I can use this as being the defining equation for the event horizon. When I have an equation like this, I can find out what the normal vector to the horizon is. So basically, I just want to go through a few steps that will show that xi is the normal vector to the horizon, so that we have the usual situation of xi being both normal and tangent to the horizon. So the normal to the event horizon is going to be equal to the gradient of that defining function v squared. That is equal to, well, the covariant derivative of what v squared stands for. So if I do the calculation, I get twice the metric times the killing vector times the gradient of the killing vector. This being a killing vector, so I can just rewrite this. I can rewrite this as twice C nu grad alpha C nu. This being a killing vector means that it obeys Killing's equation, which means that I can flip the ordering here with a minus sign. This is equal to minus 2C nu grad nu C alpha. Which we recognize as being the acceleration of I'm sorry, I'm not doing a good job here. Yeah, sorry, I didn't prepare this very well. I didn't think I would get this far, this far today, so I'm sort of improvising from my own notes. We're sort of running out of time anyway. So why don't we forget about this, and we'll come back next week, and I'll try to present this in a better way, because right now I'm sort of not I'm not following a very clearly defined thread, and I just need to prepare this better. So again, I apologize. I should never. It's pretty bad to do this just before an evaluation. So forget about all this, you know, and we'll do it better next time. So if you don't mind, I'll just stop here. Debbie will be here in a couple of minutes anyway. She'll do the. So I'll be better prepared this time.
Involves stuff that we haven't really gone to yet. Do you want us to end it in next week still, or?
You mean as opposed to right now, or?
As opposed to the week after, just so we have time to figure it out.
Oh, yeah. So let's see. So there is this. Yeah, I forget what the. Oh yeah, there was the stuff about the first law. Yeah, okay, you can hand it the week after. That's fine. Yeah, that's true. We're a little bit early in terms of material, so we won't have to do everything. We won't be able to do everything. Yeah, so yeah, the week after. So you can hand it in the week after. Okay, I see Debbie's here, so I'll leave you with her.